Welcome back to the Mechanics of Solids lecture series. In this series of videos, we're looking at examples calculating shear in built-up beams. The problem that we're looking at in this video was set up in the previous video. I paused briefly to show the problem statement and the picture of both the beam and the cross-section. I encourage you to pause, reread the problem statement if necessary, or go back and review the previous video. We'll move ahead and summarize what we know. There's three different criteria. The allowable bending stress, which is going to be determined by normal stresses in the flanges, is 1500 psi. The allowable shear stress, which is going to be determined by shear across the web, is 300 psi. And the allowable stress in the bolts is allowable shear stress in the bolts is 6000 psi, which is going to be determined by shear across the connection. The length of the beam is 15 feet. The spacing of the bolts is 9 inches, and the bolt diameter is 3/8 of an inch, or 0.375 inches. And we derived three different criteria for allowable P, one based on bending stress, one based on shear stress at the neutral axis, and one based on shear stress in the bolt. And it's important to note here that the lowest P is going to govern the overall design. Why is that? Because each of these gives a criteria for a maximum P allowable for that particular criterion to be satisfied. In order for all of them to be satisfied, we need to take the lowest P. So we'll say lowest P allowable governs the design. So we'll go ahead and go through the calculations, starting with the first one. P allowable equals 4I over LC times sigma allowable. To compute this, we need to compute the moment of inertia for the section as well as the C value. Let's go ahead to where I've drawn a picture of the section and we can compute the geometry values that we need. For the moment of inertia, we'll use the formula for a box section. We'll take I equals I outer minus I inner, which is I of the hollow part in the middle, using the rectangular formula I equals BH cubed over 12. The outer moment of inertia, we'll take the outer dimensions, 4 inches for the width, 24 for the height. So we have 4 times 24 cubed over 12, minus the inner dimensions, which is 3 for the width, 16 for the height, so we have 3 times 16 cubed over 12. This is going to be inches to the fourth, and the value computes to 3584 inches to the fourth. So that's I for our section. That's all we need for the first calculation, along with a value of C, which by inspection should be half of the total height, or 12 inches. So let's return and compute this. P allowable, based on bending, is 4 times the value of I we just computed, 3584 inches to the fourth, divided by the length of the beam, 15 feet, but we'll convert it to inches. So 15 times 12 inches. And then the C value, which we said was also 12 inches, and we'll multiply that by sigma allowable, which is 1500 psi. This computes to 9956 pounds, or if you prefer, 9.96 kips. Okay, second criteria, P allowable equals 2IT over Q at the neutral axis times tau allowable. Let's flip ahead to the picture of our section and use the first one to compute Q for shear at the neutral axis. So the area that I want to consider is everything above a cut at the neutral axis. It would be this area right here that I've drawn in. Let's label the web as section 1, and on top the flange as section 2, with the lines separating the sections as shown. Okay, so Q at the neutral axis, we'll start with the area of section 1. We have two of them, and they have an area of 0.5 times the height of 12. And then we need the distance to the neutral axis, which is half of that height, half of 12. It's going to be right up here. Sorry, this is a distance from the neutral axis to the centroid of this area right here. That is going to be 6 inches. So times 6 inches. Plus, I'll go ahead and put this on another line, the contribution from section 2, its area, which is 4 times 3, times the distance up to its centroid, which if I draw a line here, should be 8 plus half of 4, or 10 inches. So that's times 10. And sorry, I put inconsistent about my inches here, but notice that the areas are inches squared times the centroids inches cubed, or inches, so I get total units of inches cubed, and this computes to 192 inches cubed. So that's Q for the neutral axis. Okay, return to the previous slide where we're doing the calculations. P allowable equals 2 times I, we computed as 3584 inches to the fourth, times T. T is the total width across that interface, which is 2 times 0.5, or 1 inch. So just 1 inch there, divided by Q at the neutral axis, which we computed as 192 inches cubed, times our tau allowable, 300 psi, and this gives a value of 11,200 pounds, or if you prefer, 11.2 kips. Okay, last criteria. P allowable based on shear at the connection, shear flow at the connection. The only other thing we need to compute for this one is Q at the connection. This is a different Q because we're considering shear across this interface right here. So we need to isolate the area on either side of that interface. We're going to use just this area. Note that it's the same as area 2 that we did in the previous example. So we can compute that real quickly as 4 times 3 times 10. That was the contribution from 2 earlier. And that equals 120 inches cubed. So there's Q for our connection. Okay, so returning, we can complete this calculation. P allowable equals 4 times 3584 for I, times tau allowable stress in the bolt, 6,000 psi, times the area of the bolt, which we'll take as pi over 4 times its diameter cubed. We need to square that, inches squared, divided by Q at the connection, 120 inches cubed, which we just computed, and S of 9 inches. This gives a value of 8796 pounds, or if we prefer, 8.8 kips. Okay, so if we look at those, the lowest one controls, that would indeed be the shear in the bolt, the 8.8 kips. So P allowable is, let's say, 8,800 pounds, or 8.8 kips. Okay, so that's the answer to the first part. The second part was, given that value of P, let's go back and compute the actual bending stress, the actual shear stress, and the actual shear in the bolt. So I'm going to skip ahead here and remind us of what we know so far, P allowable, the sigma allowable values, and then the 3 criteria, 3 things that we're trying to compute. We need the actual bending stress, sigma max, which is equal to MC over I, where before M was equal to PL over 4 times C over I. This time we're going to use the actual value of P that we calculated, 8,800 pounds, times the L of 15 times 12 inches, times the C of 12 inches, divided by 4 times I, 3584 inches to the fourth, gives us sigma max of 1330 psi. Okay, this is lower than sigma allowable because this one did not control the design. The second one, what is the max shear in the web? I'll call that tau max. Tau max equals V, Q at the neutral axis, divided by IT, where V was equal to P over 2, Q at the neutral axis, divided by IT. Plugging in the values, 8,800 pounds, sorry, that's an 8,800 pounds for P, divided by 2 times Q at the neutral axis was 192 inches cubed, divided by I, 3584 inches to the fourth, times T, that total thickness across the connection interface of 1 inch, and that computes to 236 psi. That's the maximum shear. It's less than the allowable shear of 300 psi because this did not control the design. The third one, tau in the bolt, we do not need to recompute this one. This was the one that controlled our design, controlled our allowable stress, so tau in the bolt will be the allowable value of 6,000 psi. And that summarizes the problem. The answers make sense because all two of them are slightly less than the allowable values. It's a confirmation that we most likely did the calculations correct all the way through. And that concludes this example.